Okay guys, as we start this is kind of one of those hold on to your butts as I enter this, and just kind of bear with me a little bit, okay? So what I want to start with is remember something from pre-cal that you talked about, which is how to find an area of a sector. Now, we know that the area of a circle is pi r squared, right? But what if I only want part of that circle? Well, then instead of pi r squared, okay, well then go pee. Sorry guys. Instead of pi r squared, we're basically going to take pi out of the whole circle, okay, where we're going to take theta out of the whole circle times pi r squared. So basically it's like taking pi r squared and multiplying it by a percentage. Now if theta is measured in radians, remember a whole circle could be 360 degrees or a whole circle could be 2 pi. So if we're talking about this being in radians, which 99% of the time we are in radian mode, this formula is going to look like theta over 2 pi times pi r squared. So again, this is representing what fraction of the circle are we dealing with. Now we could simplify this by canceling our pi's and just getting 1/2 r squared theta. And this is the area of a sector formula that you should have learned in pre-cal, okay? Now let's say that we're going to say that this is a function and let r be equal to f of theta, some function of theta, okay? What we want to do is look at this function on an interval, maybe say from A to B, okay? So let's pretend that this right here is my function, okay, some polar curve, and we want to look at the area of a piece of this under this curve. Now, in land of non-polar, like typically when we're looking at a non-polar function, here's A, here's B, and we want to find the area under this curve, right? In polar land, keep in mind, we're talking about a polar defined function on this polar graph paper. We are measuring some polar function. Let's say I have some, I don't know, we'll make it a cardioid, a really bad cardioid. This cardioid is going to be defined from some angle to another angle, and we're going to be finding an area of a piece of that cardioid. That's a really, really terrible, terrible graph. Okay, so let me give you another example. Okay, let's do, let me show you a little bit better drawing. All right, here is this cardioid. Okay, instead of showing on polar graph paper, remember this line right here represents an angle of 0, and this line right here represents an angle of pi. So when we talk about taking a sector of this graph, let's say we want the area of this thing from pi fourths to, let's make this 3 pi fourths. The problem with this is not area from x value to x value. This is area from theta 1 to theta 2. So we're literally talking about taking an area over a range of values of an angle. Okay, so now back to our notes. Okay, so we're taking this from theta 1 to theta 2. Now in our Riemann sum land, when we did area of a rectangular function, okay, so an area from A to B of some function, and we would partition this into infinitely many rectangles, right? And we found the Riemann sum of those infinitely many rectangles, making our theta, or making our subintervals infinitesimally small. The problem is, in polar land, we're not talking about rectangles anymore. We're actually talking about little tiny slices of an angle, infinitesimally many slices of this angle along this polar curve, okay? And making as many slices as we possibly can. Now, there's some more complicated pictures of these infinitely many slices right here that you can most certainly look at. but I don't want you worried about that, okay? So we could technically say that this area could be approximated by the sum of infinitely many, I equals 1 to n, slices of 1/2. Instead of r squared, we're going to say f of theta, because that's a function, but we're going to square it, okay, times delta theta, okay? And what this is basically saying is infinitely many partitions, okay, infinitely many partitions of little tiny, tiny, tiny angles. And again, I'm using f of theta because we're saying that r squared is f of theta, so I'm basically plugging that into this formula, okay? Again, this is like a hold on to your butt moment as I go through this, okay? So I can't take infinitely many subintervals, so we need a limit to really be able to say that, a limit as n approaches infinity. Now, whenever I write anything scary, immediately you guys are thinking, gosh, I'm going to have to replicate this. And you don't. I'm just trying to prove a point. So I equals 1 to n, 1/2. I'm going to use that f of theta. We're still going to square it, delta theta. Just like we took infinitely many rectangles, I'm now saying infinitely many subintervals. But remember that when we're using this notation, this is a notation for an integral. So really, I can say that this is now the area from A to B of 1/2 f of theta squared d theta. Or in other words, we now have derived a formula that area is equal to 1/2 integral from A to B of r squared d theta. Now you might be going, well, why is it r squared d theta? Because again, our function is going to be some r of theta. So we've now got a formula for area. Anytime you are asked to find the area bounded by a polar curve of some function r from theta to theta, we're going to use the formula area equals 1/2 integral from alpha to beta of r squared d theta. You need to draw a big star around this because this is ultimately what you're going to be expected to do in polar land and calculus. In calculus, the most important thing that you will learn to do and be able to be asked to do on the AP exam is to find the area under polar curves. You're going to have to make sketches and find the area. So let's walk through a couple of examples. Sketch the graph of r equals 2 plus 2 sine theta and find the area bounded by the curve. Now, you would have to do this without a calculator. Step one, I'm looking at this and I go, hey, A equals B, this is a cardioid, okay? So I know I have a cardioid. The next thing I notice is that it's a sine function, which means it's going to be symmetric over y. So I know it's going to be symmetric over y. To get a few points, I can kind of plug in some points, and I'm going to do this mentally, but I'm writing out this table of values for you, not me, for you. So let's start with 0. If I plug in 0, the sine of 0 is 0. 0 times 2 is 0. And so I get the point 2, 0. So that means that I am at a radius of 2 at an angle of 0. Okay? I'm going to plug in pi halves just to get a general shape of this graph. Sine of pi halves is 1. 1 times 2 is 2. 2 plus 2 is 4. So at my angle of pi halves, which remember this is my angle of pi halves, I'm up at a radius of 4. Now I know that this is symmetric over y because it's a sine graph. So I immediately know that this is going to have a point over here. And I could test another point if I really wanted to, like I could test 3 pi halves. If I plug in 3 pi halves, sine of 3 pi halves is -1. -1 times 2 is -2. -2 plus 2 is 0. So I know that this thing is going to do that and make my cardioid shape. Okay, now I want the area bounded by this graph. Now you need to keep in mind that the area bounded by this graph, they're talking about starting at an angle of 0 and wrapping all the way around and finding all of this area. Now you're noticing that I'm extending out because this is what's happening to my radius as I go through different angles of theta. Okay, so we're going to find the area of this curve. Okay, now my area formula that we just derived is that area is equal to 1/2 integral from alpha to beta of r squared d theta. So in this case, I'm going to go 1/2. I want the entire area, so this thing goes from 0 to 2 pi. And I'm going to take my function 2 plus 2 sine theta. I'm going to square it, d theta. Okay? Now in this case, you would be expected to do something like this by hand. Sure, you could plug this into the calculator. Okay? But let's remember a couple of things. First off, I'm going to use this fact in a minute. I'm going to use a power reduction identity in a minute. And remember that sine squared x is equal to 1/2 1 minus cosine of 2x. And that cosine squared x is equal to 1/2 1 plus cosine of 2x. And these are my power reduction identities. Okay, so I'm going to actually multiply this thing out. I'm going to get area equals 1/2 integral from 0 to 2 pi. Let's expand this thing out and we get 4 plus 8 sine theta plus 4 sine squared theta d theta. Okay, and again, that's because we're going to have, you can FOIL that out on your own. You could do that. Okay, so I'm going to distribute this 1/2 in to make my life easier and my numbers a little bit prettier. And I'm going to get the integral from 0 to 2 pi. Okay, of 2 plus 4 sine theta plus 2 sine squared theta d theta. Okay, because I can take the integral of this and I can take the integral of that, I cannot take the integral of that. This is where I'm going to use a power reduction identity to make my life easier. So integral from 0 to 2 pi of 2 plus 4 sine theta plus 2, and I'm going to turn this guy into 1/2 1 minus cosine of 2x d theta. Immediately these cancel out and go away. And I continue this by hand and go ahead and take the antiderivative. So the antiderivative of 2 is going to in fact be 2 theta. The antiderivative of 4 sine theta is going to be negative 4 cosine theta. And then the antiderivative of this is going to be another plus 1 theta. And then my antiderivative of negative cosine of 2x is going to be negative 1/2. I ran out of room. Sine of 2 theta. And you're going to take this and evaluate it from 0 to 2 pi. Yes, I know you can combine the 2 theta and the 1 theta to get 3 theta. I want you to press pause and go ahead and evaluate that. If you're coming back, hopefully if you did this right, you got an answer of 6 pi when you plugged it all in. I ran out of room, okay? I ran out of room. I want you to write yourself a note. Anytime you have a cardioid or a limison, you're going to go from 0 to 2 pi. That's where our integral will always be evaluated. So anytime you have a cardioid or a limison, you're going to go from 0 to 2 pi. 0 to 2 pi, okay? I want to walk through another one with you, and this one's kind of nice because it's a rose curve, and you need to be able to do this by just setting it up. All this question asks for you to do is to sketch and set it up and do not evaluate, which makes this a really, really nice question. Okay, so remember R and theta. I know this is a rose curve that's going to be symmetric over Y. I know that it's going to have 3 petals, and I know that this thing is going to extend out to a radius of 2. So what I need to figure out is if this is symmetric over Y, does my 1 petal go up here and 2 petals go up here? Or is it that 1 petal goes up here and 2 petals go down here? So here's how you're going to decide that, okay? All right, so I'm going to test a point. I'm going to first start by testing 0. Sine of 3 times 0 is 0, sine of 0 is 0, and I get 0 times 2 is 0, so this thing is starting at 0, 0. Doesn't really tell me a whole lot. But then I'm going to kind of be thinking about pi fourths to basically see, is there a petal jutting out on that side? So if I plug in pi fourths, I get sine of 3 pi fourths, which is in fact root 2 over 2, and then 2 times root 2 over 2 is going to cancel out those 2's, and it's going to give me root 2, which is 1.41. So there is a petal kind of extending out in this way, which means if there's a petal extending out that way, that my symmetry petal is down here, and I have another petal kind of out here, okay? And I'm not going to continue going through my thetas to be able to prove that. You can most certainly graph it and verify that. Okay, but this is kind of an interesting question because it says we want to write the area of 1 petal, only 1 petal. Okay, so whenever you're graphing a rose curve, what's kind of cool about a rose curve is this thing is going to go here, and then it's actually going to go down here, and then it's going to go over here. And to prove that to you, I want to show you in a calculator kind of the path of this thing, which I think is really cool. You're going to go 2 sine of 3 theta, and I want you to go over here and change this so you get the little path doohickey. Oh, I keep passing it. There it is. And I think I had my window set up kind of funny. So let's go from 0 to 2 pi. And let's zoom 6 this. Let me zoom in just a little bit. Pay attention to how many times this thing goes around. So there's 1 petal, 2 petals, 3 petals, and this thing actually goes around twice. So I had my window from 0 to 2 pi. This thing actually completes 1 full turn by the time it's through pi. So 0, let's change the max to pi. Here's 1 leaf, 2 leaves, 3 leaves, and it's already made the whole darn thing. So this rose petal, this rose curve has a domain of 0 to pi, okay? So how will I find the area of just 1 petal? Now, sure, you could find the area of the whole thing and then divide it by 3. That would work. But do you notice every time it goes back to the origin? So it's going around the petal curve, back to the origin, down here, back to the origin, down here, back to the origin. So what if I took my 2 sine of 3 theta and set this thing equal to 0? If I do that, that's going to give me sine of 3 theta equals 0. Now, where is everywhere where the sine function is equal to 0? Well, the sine function is equal to 0, basically negative 2 pi, negative pi, 0, pi, 2 pi, and this thing goes on forever and forever, right? So what that tells me is that 3 theta is equal to that. So if I want to solve for theta, divide all of these by 3, and I now have everywhere where this thing goes back to the origin. So if I want one petal essentially is every time it goes from origin to origin. So I'm going to pick those two, and that's going to represent one petal. So I now have enough to write my area expression. I'm going to find 1/2, because that's part of my area formula, integral from 0 to pi thirds of my r to sine 3 theta. This thing gets squared, and I've now answered the question. I've set up an expression for the area of one petal. Okay, let's do one more and call it a day. Sketch and set up an integral expression for the area, again, of one petal of 4 cosine 2 theta. Okay, things I know right off the bat. This is a rose curve. It's cosine, so it's symmetric over x. It has an n that's even right there, so we're going to double that. It has 4 petals. And I don't even need to go through a sketch of this because I know that it's going to extend to 4 here. It's going to extend to 4 here, to 4 here, and to 4 here, and is going to basically do this number and have 4 petals. One of the things that I think is kind of interesting, though, is to see this graphed with a path to know kind of the path it's taking. Now, on the AP exam, and if this was a non-calculator question, which it very well could be, okay, you could easily do this by making a table of values, but let's go back here and make a path. And let's go to our window and go from 0 to 2 pi and zoom 6 this. So there's 1 leaf, 2 leaves, 3 leaves, 4 leaves. And notice, let me show you that graph one more time. Watch the particle. Top, down, left, here, and then it completes it down underneath, which is kind of interesting. So this rose petal actually went from 0 to 2 pi, which is kind of cool. All right. So how do I find one petal? Notice again, every time it returns to the origin. So this thing goes, this top, and excuse me, it started here, top, and went down, and here, and then finally came back and completed it. Every time it referred back to the origin. So why don't we take our function for cosine of 2 theta and find when it equals 0, aka the origin. So that means that cosine of 2 theta equals 0. So where is everywhere that cosine equals 0? Well, cosine equals 0 at negative pi halves, at pi halves, at 3 pi halves, at other pi halves values. So that means that 2 theta is equal to those solutions. So how do I get theta? Take all of these and divide by 2, divide by 2, divide by 2, divide by 2. And that means that it's going to happen at negative pi fourths, positive pi fourths, 3 pi fourths, and so on. So one petal is essentially going to be one rotation from origin to origin. So if I take this, that's one petal. I can now write my integral. 1/2 integral from negative pi fourths to pi fourths of my r for cosine 2 theta, and then this thing gets squared d theta, and I have the area of 1 petal. Okay? You could easily just go from 0 to pi fourths and double this for symmetry, but we're going to stop there. You need to come into class ready to work. You need to come in kind of prepared mentally with questions, and we're going to tackle some pretty tricky overlapping polar curves and then do a couple more examples, and we will be finished with content, guys.